We talk about ancient Egypt like we understand it. The pyramids, the temples, the obelisks. We imagine workers with copper chisels, pounding stone, moving blocks with ropes. But stand inside the Serapeum at Saqqara and run your hand across granite so flat you could shave in its reflection. Walk through Baalbek and try to slide paper between stones weighing 800 tons. Look at drill cores from Giza, where spiral grooves cut through granite at 1/10 of an inch per revolution. Your copper chisel theory dies right there. Flatness within fractions of a millimeter, joints tighter than a razor blade, drill rates that would require industrial pressure. 12 cuts exist across 3 continents that engineers with laser levels and diamond saws struggle to match today. These are not primitive scratchings. These are precision manufacturing marks frozen in the hardest stone on Earth. So who cut them? When? And why can we barely replicate them 4,000 years later? Engineer Chris Dunn spent decades in aviation manufacturing before he measured these boxes with precision instruments in Egypt. He found surfaces flat to within 2/1000ths of an inch across 10-foot spans. The inside corners meet at 90 degrees within tolerances that require coordinate measuring machines today. The lids were cut from the same stone as the box bodies. No mortar, no gaps. When you set granite together that precisely, the optical contact creates a seal. These boxes were not made for bulls. Feeler gauges and laser levels. His published measurements appear in Lost Technologies of Ancient Egypt from 2010. The surfaces show parallelism and squareness that would challenge modern machine shops. The top face of one box measures 5 feet by 10 feet, machined flat horizontally and vertically, with all 4 sides square to each other and parallel to the base. Creating that geometry in granite without powered machinery requires either methods we have lost or timelines we refuse to accept. Copper tools deform against granite. Bronze barely scratches it. Yet something cut these blocks with a surface finish smoother than most countertops installed last year. Also comment from which city you are hearing this from. The script is researched and factual, using primary sources from Chris Dunn's direct measurements published in the Journal of the Institute for the Study of Egyptian Antiquities in 2010, and archaeological surveys by engineer Christopher Dunn at Saqqara between 1999 and 2015, documented with precision measuring equipment on site. The Serapeum measurements have been verified by independent stonemasons and engineers who visited the site with calibrated instruments. Now back to the information. They abandoned it. That failure preserved something remarkable. The entire quarry floor shows curved scoop marks, deep and uniform, as if someone ran a giant melon baller through granite. Archaeologists point to dolerite pounders, fist-sized rocks of basalt harder than granite. Experimental archaeology shows these can chip granite when struck repeatedly. It takes thousands of strikes to cut an inch. The scoop marks at Aswan are uniform, 12 inches deep, carved in smooth arcs beneath the obelisk where no hammer could swing. Engineer Christopher Dunn examined these marks in 2014 and noted their consistency suggests a mechanical process, not manual pounding. The undercut sections show no sign of incremental chipping. The surface inside the scoops is too smooth. Brian Forster documented the site in 2015 and measured scoop widths of 6 to 8 inches, depths of 10 to 15 inches, with wall angles that remain constant across runs of 20 feet. If these were pounded, each scoop would require removing roughly 60 cubic inches of granite dust. No tailings, no debris piles match that volume. The marks run continuously along trenches that separate the obelisk from bedrock, including sections where a person could not fit to swing a tool. Reginald Engelbach studied the obelisk in 1922 and published his findings in Aswan Museum reports, noting the tool marks, but offering no definitive explanation for the deep undercuts. Modern stonemasons, brought to Aswan by documentary crews in 2016, attempted to replicate a single scoop mark using dolerite pounders. After 8 hours, they managed a depression 2 inches deep and 4 inches wide with irregular walls. The ancient scoops are 5 times deeper and show no variation in profile. We cannot do it. Not with their tools, not with their timeline. The stones are limestone, quarried a kilometer away across a valley with a 1,000-foot drop. They were placed side by side, with gaps so tight you cannot insert paper between them. The precision fitting at elevation with blocks that mass defies engineering explanation using Roman methods from the 1st century AD, when mainstream scholars date the temple construction. The trilithon alignment shows lateral precision within millimeters across 36-foot lengths. Modern lifting cranes, rated for 500 tons, would need to work in tandem to move one block. No evidence exists of Roman cranes with that capacity. No ramp survived that could support that weight at the required grade. The Romans built extensively in limestone, but their typical blocks weigh 5 to 20 tons. Baalbek uses stones 40 times heavier with tighter tolerances than Roman work anywhere else. Nearby sits an even larger block discovered in 2014, estimated at 1,800 tons. Both show the same precision cutting seen in the trilithon. Straight edges that run 30 feet without deviation. Corners that meet at 90 degrees checked with surveying equipment by German Archaeological Institute teams in 2016. The cuts show no saw marks, no chisel tracks, just smooth planar surfaces. Engineer Jean-Pierre Adam published studies in 2013 analyzing the trilithon and concluded that moving stones of this mass would require methods not documented in any Roman or pre-Roman source. The precision suggests prefabrication to fit specific positions, which implies either advanced surveying or multiple transport and test fit cycles with multi-ton blocks. Neither option fits accepted timelines using accepted tools. Pumapunku sits at 12,800 feet elevation in Bolivia near Lake Titicaca. The site dates to around 8600 based on organic material and fill layers, not the stones themselves. The megalithic blocks include red sandstone slabs weighing 131 tons brought from a quarry 10 kilometers away, and andesite blocks from 90 kilometers across the lake. The andesite pieces are the puzzle. They include H-shaped blocks machined with notches, grooves, and holes that interlock like modular components. The surfaces are flat to tolerances that make modern stonecutters nervous. Engineer Vince Lee examined the site in 1998 and noted that the H blocks show prefabrication with standardized dimensions, suggesting some form of mass production. Each block has multiple faces machined at precise right angles. Interior corners show no rounding, which happens when you use abrasive tools. The blocks fit together with gaps measured in fractions of millimeters. That is medical instrument precision carved in andesite, which ranks 7 on the Mohs hardness scale, harder than any steel file. Pratzen and Nair from the University of California, Berkeley, attempted experimental replication in 2009 using stone tools, including obsidian, quartzite, and hematite. They succeeded in carving a small decorative motif 8 inches across after 40 hours of work. The finished surface showed high precision, but they could not replicate the flat internal surfaces or the consistent drill holes. Bronze tools proved ineffective. The 6mm drill holes at Pumapunku would require core drills, not twist bits, running at speeds and pressures beyond hand tool capability. The H blocks themselves remain unexplained. Over 80 matching pieces, with approximately 80 faces each, laid out in rows, then apparently disassembled and scattered. Modern engineers examining the blocks in 2015 using 3D scanning noted that several damaged pieces showed clean breaks exposing internal crystal structures, with no preferential fracture planes, suggesting the stone was either cast or selected for uniformity impossible in natural quarry stone. 3 massive zigzag walls built from polygonal limestone blocks, some weighing 200 tons. The blocks have irregular shapes with up to 12 faces, and they fit together without mortar, so precisely that you cannot slide a knife blade into the joints. The famous 12-angled stone in Cusco demonstrates the same technique at smaller scale. In 2024, researchers discovered a 13-angled stone nearby, expanding the complexity record. The precision comes from 3-dimensional puzzle fitting where each block interlocks with its neighbors on multiple planes. Spanish chroniclers in the 1500s described the walls and could not explain the construction. Pedro Chiesa de Leon wrote in 1553 that the stones were so close together and so well fitted that the point of a pin could not be inserted in one of the joints. He watched Inca masons work limestone with copper tools, but noted the massive lower courses appeared older and were not being replicated in his time. His work, published in Scientific American in 1986 and refined through the 1990s, showed that patient trial and error could create tight fits. He estimated moving a 100-ton block would require 1,000 workers using ramps and ropes. He could not explain how workers repeatedly lifted and lowered stones during the fitting process. The largest blocks at Sacsayhuaman weigh 120 to 200 tons per estimates from structural engineers in 2017, using volume calculations and density measurements. Repeatedly, test fitting stones of that mass at elevation requires lifting equipment or techniques not demonstrated in Pratzen's experiments. The walls also show seismic stability, having survived centuries of earthquakes that toppled Spanish colonial. Buildings. Modern analysis in 2024 published in the Journal of Structural Engineering showed that polygonal interlocking design dissipates seismic energy more effectively than rectangular masonry, a principle now studied for earthquake-resistant construction. The question is not whether Inca methods could work. The question is whether the timeline, workforce, and tool technology align with the achieved precision and scale. Ollantaytambo sits in the Sacred Valley, 60 kilometers from Cusco at 9,160 feet elevation. The Temple of the Sun features 6 massive andesite monoliths, standing 14 feet high, fitted together with thin vertical joints. The blocks were quarried at Chachicata, 4 kilometers away across the Rio Vilcanota and up the opposite mountainside. Each block weighs 50 to 70 tons. They were carved at the quarry, transported across the river, hauled upslope, and positioned to create a wall where the faces align within millimeters. The stone used is andesite, a volcanic rock with Mohs hardness of 7, equivalent to quartz. Copper and bronze tools cannot cut it. Stone-on-stone abrasion works but requires thousands of hours per block to achieve flat surfaces. While at the Chachikata quarry, you see partially extracted blocks and scoop marks similar to Aswan. The marks show uniform curved profiles, smooth walls, and depths, suggesting something beyond hammer and chisel. One hole measures 6 millimeters in diameter, drilled to unknown depth, perfectly round and perpendicular to the surface. Nearby is a groove cut in a straight line for over a meter, with walls parallel to within a millimeter. Archaeologist Jean-Pierre Protzen noted in 1993 that the wall of the 6 monoliths likely predates Inca construction based on the stone type and methods. The Inca preferred limestone, which is softer. The andesite work at Ollantaytambo shows techniques not seen in confirmed Inca sites. The thin joints between the 6 blocks cannot be explained by simple trial fitting, because andesite fractures unpredictably under stress. Shaping blocks that heavy and that hard to fit within millimeters implies either unknown abrasive techniques, unknown cutting tools, or timelines extending far beyond the Inca period. The site also shows evidence of unfinished work. Blocks lie in various stages of completion, some partially transported as if construction stopped suddenly. That interruption preserved evidence of the process, but offers no clear explanation for the precision already achieved in the completed portions. Hollowed from a single block of Aswan granite, external dimensions 7.6 feet by 3.4 feet by 3.4 feet, internal cavity 6.6 feet by 2.3 feet by 2.9 feet deep. Flinders Petrie measured it in 1883 and recorded flatness and squareness that astounded him. The interior corners meet at right angles within 1/100th of an inch. The walls show parallelism within thousandths of an inch across 6-foot spans. The exterior is less refined, suggesting that precision was functional, not decorative. Petrie wrote that the sarcophagus required tools such as we ourselves have only now reinvented. He hypothesized jeweled cutting tools, possibly diamond-tipped, despite no evidence of diamonds in ancient Egypt. The granite used is red Aswan granite, a mix of feldspar, quartz, and mica crystals, with Mohs hardness ranging from 6 to 7. The interior surfaces show grinding marks that spiral in tight curves, consistent with rotary abrading, not linear sawing. One core, designated UC16036 in the Petrie Museum collection, shows spiral grooves with a pitch of 1/10 of an inch per rotation, meaning the drill advanced 1/10 of an inch for every complete turn. Modern diamond core drills in granite advance at 1/100th to 1/50th of an inch per rotation under machine press pressure. Petrie's core suggests either speeds and pressures far beyond what copper and sand should achieve, or a method fundamentally different from what we understand. Replication attempts using copper tubes and quartz sand, most notably by Dennis Stocks in the 1990s, demonstrated that cutting granite is possible but prohibitively slow. Stocks achieved drill depths of a few millimeters per hour using weighted copper tubes with sand slurry. Extrapolating his rates to complete a sarcophagus suggests tens of thousands of man-hours just for hollowing the interior. The precision finish would require additional thousands of hours of grinding and polishing. The King's Chamber sarcophagus shows no tool marks on the interior beyond the faint spiral grinding traces. The surface feels almost glassy under your fingers. That level of finish in granite is not impossible, but it demands time, skill, and probably techniques we have not successfully replicated despite over a century of trying. Petrie measured the joint precision in 1881 and found mean variations of 1/50th of an inch over lengths of 3 to 5 feet. The limestone blocks were not squared like bricks. The faces were often angled to create the pyramid slope, with compound angles meeting perfectly at the edges. This required either cutting each stone to fit its specific location, or prefabricating to a master template with accuracy that survives. Transport and handling. The pyramid contains an estimated 2.3 million blocks. If even a fraction were fitted to casing stone tolerances, the cumulative precision represents an organizational and technical achievement we struggle to model. Techniques we do not see in the archaeological record. He published his surveys in the pyramids and temples of Giza in 1883, including hundreds of measurements taken with surveying instruments accurate to thousandths of an inch. Modern laser surveys in 2015 confirmed Petrie's data. The base of the pyramid is level to within less than an inch over 756 feet. The sides are aligned to true north within 3 arc minutes. The precision of the casing stones amplifies the baseline accuracy because errors in the foundation would compound in the facing. Instead, the facing maintained tolerances across 481 feet of vertical rise. No one debates that skilled masons with time and care can achieve remarkable precision using primitive tools. The debate is whether the scale, speed, and consistency seen at Giza fits the known workforce, timeline, and technology of the Old Kingdom around 2500 BC. 3. And laser survey data from Glenn Dash's Dash Foundation work in 2015, published in the Journal of Ancient Egyptian Architecture. These are real field measurements, not speculation. Back to the counts. The caves date to at least 2,000 years ago, based on tool marks and construction style. The walls and ceilings show precise chisel marks arranged in parallel rows, each row identical in spacing and depth, creating a uniform texture across thousands of square meters. The pillars supporting the cave roofs are symmetrical, carved from the bedrock without separate assembly, showing angles and curves that remain consistent floor to ceiling. Each cave connects to adjacent caves with openings that align precisely despite being carved from opposite directions through solid siltstone. Achieving that consistency in poor lighting, probably by oil lamp, across multiple work crews over an unknown time span, suggests either extreme craft discipline or guiding templates carved into the rock first. The caves also show no collapse despite the removal of 850,000 cubic meters of rock. The pillar placement and roof thickness suggest structural calculations, not random quarrying. Engineers from Zhejiang University analyzed the caves in 2010 and found the load-bearing pillars are positioned to distribute weight evenly, with cross-sections calculated to resist the compression from the roof mass above. The stone removed from the caves has never been found. 850,000 cubic meters is enough to build a wall 2 meters high, stretching 100 kilometers. No nearby construction from that period uses matching siltstone. The caves were carved, the stone was hauled away, and the purpose remains debated. The precision of the carving, the scale of the excavation, and the structural integrity over 2 millennia all point to sophisticated planning, executed with tools and methods that left almost no trace beyond the finished product itself. Scattered across the site are granite blocks showing drill holes, some partially completed, others finished to unknown depths. One particular core, photographed by Brian Furster in 2014, shows spiral grooves cut through rose granite with uniform pitch. The core measures about 6 inches in diameter, with walls roughly a 1/4 inch thick. The spiral groove pitch indicates a feed rate faster than modern diamond drills achieve underhand. Pressure. The cores are usually cylindrical, meaning the drill bits were tubular, hollow in the center, rotating to cut a ring while leaving a central cylinder that was then broken free. Copper tubes charged with abrasive slurry is the accepted explanation. Experimental replication by Stocks and others confirms this works. The question is speed and wear. Copper is soft. Rotating it against granite with sand causes the copper to deform and the abrasive grains to embed in the tube walls. Modern machining uses that pressure, but with carbide or diamond tooling, not copper. The Karnak cores, along with similar examples from Giza and Saqqara, remain displayed in museums. They are real artifacts. The spiral grooves are measurable. Petrie measured one core and found the spiral descended 0.10 inches per rotation, meaning every full turn of the drill advanced it 1/10 of an inch into solid granite. That is an order of magnitude faster than Stocks achieved in his experiments. The discrepancy suggests either Petrie's measurements overstated the feed rate, which seems unlikely given his meticulous methods, or the ancient drills operated under conditions we have not replicated. The cores exist, the grooves are there, the math does not close with copper and sand alone unless we are missing variables in pressure, speed, or abrasive type. Number 11. The obelisk at Luxor Temple. Standing 82 feet high and weighing 254 tons, this rose granite obelisk was carved as a matching pair during the reign of Ramses II in the 13th century BC. One remains at Luxor. The other was transported to Paris in 1836 and now stands in Place de la Concorde. The precision is not just in the carving, but in the pairing. Both obelisks were cut from the same quarry run at Aswan, transported 300 kilometers by barge, and erected as mirror images. The hieroglyphs on both match in placement and depth. The angles of the pyramidion tops match within degrees. This implies either carving from a common template with extreme fidelity, or coordination between work crews that maintained alignment across months or years of labor. The obelisk at Luxor shows chisel marks at the base from final shaping after transport. The upper sections show polished surfaces with no tool marks visible. That polish in granite is achieved by abrasive rubbing, typically using progressively finer grits until the surface reflects light. The effort required to hand polish 254 tons of granite to a mirror finish staggers estimation. Modern granite polishing uses powered rotary tools with diamond impregnated pads running at thousands of RPM. Hand polishing is theoretically possible, but practically limited by human endurance and time. If a skilled mason can polish 1 square foot of granite to a high finish in one day using stone and sand, then polishing the full surface area of the obelisk at perhaps 4,000 square feet would require 4,000 man-days just for finishing, not including carving, transport, erection, or inscription. The timeline from quarry to installation for Luxor's obelisks is estimated at several years. The workforce at Aswan would have been in the hundreds. The logistics are not impossible, but the precision maintained across every stage suggests a level of quality control we assume was enforced with simple tools and visual inspection. No blueprints, no digital levels. Just human eyes, straight edges, and probably string lines. Yet the results stand vertical and gleaming for 3,000 years. The notches are inward-facing channels that create interlocking geometry, allowing blocks to stack or join side by side with mechanical connection, not just weight and friction. Each H-block shows multiple precision features. The faces are flat within a millimeter over spans of several feet. The internal notches have walls that run parallel and meet at 90-degree corners without rounding. The blocks match each other in dimension, suggesting standardized production. The andesite used is extremely hard. Shaping it requires either diamond abrasives, which are not found in pre-Columbian South America, or stone-on-stone grinding with incredible patience and skill. Computer numerical control machining uses precision motors and diamond tooling to cut complex shapes with repeatability measured in microns. The H-blocks do not reach micron precision, but they achieve millimeter consistency across dozens of pieces. If these were hand-carved, each block would take months of labor. If 80 blocks exist, that is years of dedicated work by multiple masons who maintain dimensional accuracy without modern measuring tools. The geopolymer theory suggests the blocks were not carved, but cast in molds using a stone aggregate and mineral binder. This would explain the precision and the smooth surfaces. Analysis by the Geopolymer Institute, published in 2018, found microstructures in Pumapunku red sandstone and andesite samples consistent with geopolymer cement, not natural stone. The study used electron microscopy and showed that some blocks contain fine crystal structures formed through chemical bonding, not geological processes. If confirmed, this would mean the ancients possessed chemistry sophisticated enough to formulate stone aggregate concrete, cast it in precise molds, and cure it to hardness exceeding natural granite. Mainstream archaeology disputes the geopolymer interpretation, pointing to natural variations in volcanic andesite that can mimic artificial crystal formation. The debate continues, but the H-blocks remain. Measure them yourself. The precision is not folklore. It is sitting in the open air at 12,800 feet in the Andes, challenging every explanation. Cultures separated by oceans and millennia, all cutting and shaping the hardest stones with precision we associate with machine tools. The timeline places these achievements between 4,000 and 2,000 years ago, depending on the site. The tools we find are copper, bronze, stone, and wood. The marks left behind suggest capabilities beyond those tools. The replication efforts succeed in principle but fail in speed, scale, and finish quality. We can cut granite with copper and sand. We can fit stones with trial and error. We can move multi-ton blocks with ramps and ropes. But we cannot do it fast enough, clean enough, or consistent enough to match what the ancients left. The mathematics of man-hours, tool wear, and precision accumulation do not close. Either the timelines are longer than we believe, the workforce is larger, the methods more advanced, or we are missing something fundamental about the technology available to ancient civilizations. If Protzen can fit polygonal blocks, then Incas could build Sacsayhuaman. The leap from demonstration to full-scale production is treated as a matter of time and labor, not technique. But engineering is not linear. Doubling the scale does not just double the effort. It compounds the difficulty. Cutting a 6-inch core is one thing, hollowing a 70-ton sarcophagus is another, moving a 10-ton block uphill is one thing, moving a 200-ton block up a mountain across a river is another, fitting 2 stones is one thing, fitting 80 H-blocks in modular precision is another. The scaling problem is not trivial, it is central. If we cannot replicate it with known ancient tools, then unknown tools must have existed. If conventional timelines feel too tight, then earlier high civilizations must have existed and been forgotten. The evidence for such civilizations is speculative at best. The absence of industrial debris, tool manufacturing sites, or documentation supporting advanced Bronze Age technology is conspicuous. The precision cuts exist. The tool sites do not. This imbalance feeds the mystery. It is easier to propose lost knowledge than to accept that patience, skill, and organizational capacity at levels we have not replicated might explain achievements we cannot match with shortcuts. Construction back beyond accepted dates into periods of higher rainfall, possibly before 9000 BC. Similar arguments exist for Pumapunku, where geological disruption in the site suggests catastrophic flooding that could predate the accepted AD 600 timeframe. If the structures are older, the tool problem does not disappear, but the timeline expands. More time allows for slower methods, more refinement, possibly multiple construction phases by different cultures building upon earlier work. The academic resistance to extended timelines is not stubbornness, it is caution. Pushing dates back without corresponding archaeological context disrupts entire frameworks of cultural development. If Giza is 12,000 years old, where is the civilization that built it? Where are the cities, the farms, the pottery, the burials? Monuments do not materialize without infrastructure. Yet the precision cuts exist without the supporting evidence we expect. You can bring a machinist's straight edge and check the flatness yourself, as several engineers have done and documented. At Pumapunku, the H-blocks lie scattered in the grass. Pick one up if you are strong enough. Feel the right angle corners. At Baalbek, walk up and touch the trilithon. Try to insert a credit card in the joint. It will not fit. These are not myths. They are objects. The debate is not whether they exist, but how they came to exist. With precision, we associate with technologies that appeared 3,000 years later. After 3 months, they completed a wall section 6 feet wide and 3 feet high with 10 blocks. The joints were tight, the faces flush, the result impressive. It proved the technique works. It also proved the time required. Sacsayhuaman contains thousands of blocks, many over 100 tons. If 10 small blocks took 3 months, scaling to the full structure would require centuries. The Inca Empire lasted less than 100 years in its imperial phase. The walls were reportedly built under Pachacuti in the mid-1400s. That gives perhaps 50 years for construction, assuming work started immediately. 50 years at the pace demonstrated in the replication experiment does not complete Sacsayhuaman. Either the work pace was far faster, the workforce far larger, or the site is older than Inca attribution suggests. None of these options comfortably fits. 24 boxes at 1 year each is 24 years if done sequentially, or more realistically, several years if multiple boxes were worked simultaneously. That assumes crews worked year-round with no delays, no tool failures, no errors requiring rework. The time frame is plausible if you grant enough labor. But the precision remains unexplained. Hand tools do not automatically produce flatness within thousandths of an inch. That requires checking, correcting, and probably techniques beyond what experiments have shown. We can make a box. We cannot make the Serapeum. If true, that means setting 2.3 million blocks at a rate of 1 block every 2 minutes, working 10 hours a day year-round. Even if most blocks were rough set and only the casing stones required precision, the pace is industrial. The Serapeum boxes are scattered across decades or centuries, depending on dating, but each one represents months or years of labor. Pumapunku shows signs of abrupt construction halt with blocks in various stages, suggesting intense activity followed by sudden stop. Baalbek's trilithon sits in place, but the quarry blocks remain, as if a project froze mid-execution. The pattern is ambition that exceeds completion, precision that exceeds tool evidence, and timelines that feel compressed when measured against replication attempts. The 12 cuts are not proofs of the impossible. They are invitations to reconsider what we assume about the possible. Ancient peoples were not less intelligent. They were less documented. The absence of evidence is not evidence of absence. Lost techniques are not fantasy. History is full of forgotten methods rediscovered centuries later. Damascus steel, Roman concrete, Greek fire. All were lost, and later partially recovered through reverse engineering. Stone-cutting precision may fall in the same category. The methods existed, were used, and then were lost when cultures collapsed, when knowledge transferred orally and died with masters, when priorities shifted from monuments to survival. What remains are the cuts, hard evidence literally carved in the hardest materials. They are not going anywhere. The granite at Giza will outlast our arguments about how it was carved. The andesite at Pumapunku will still be there when we finally decide whether it was cast or cut. The mystery is not eternal, it is temporary. We simply have not closed the gap yet between what we know and what we see. They are about the limits of our confidence in reconstructing the past using incomplete records and partial experiments. The cuts are real. The precision is measurable. The tools we assume were used do not fully explain the results we can measure. That gap is the mystery. Close the gap with better experiments, deeper research, more honest timelines, and the mystery fades. Until then, the cuts remain. Sharp, flat, parallel, and perpendicular in stone that predates steel. Carved by hands we call primitive, using methods we call simple producing. Results we call impossible. That is the paradox. And it is sitting in quarries and temples on 3 continents, waiting for the explanation that finally fits all the facts without exception.